In this video, we'll be covering section 11.2, arithmetic series. We have two objectives. We will be finding the sums of arithmetic series. That includes finding an explicit formula for the sum. And we will also introduce the concept of summation, or sometimes called sigma notation, to rewrite sums. So let's go ahead and get started. So first, what is a series? A series is simply an indicated sum of the terms of a sequence, meaning that if you have a sequence, any sequence, and you add the terms up, that becomes a series. Now we are looking particularly at just arithmetic series, so we're going to always be dealing with an arithmetic sequence in this section and looking at the sum of those terms. All right, let's start with an application. So this says, the first amphitheaters were built for contests between gladiators. Modern amphitheaters are usually used for performing arts. Amphitheaters generally get wider as the distance from the stage increases. Suppose a small amphitheater can seat 18 people in the first row, and each row can seat 4 more people than the previous row. Find the total number of people that can be seated in the first 5 rows. Okay, so I've started to make a table here. It said in the first row, in this row, the very first row next to the stage, 18 people can sit there. And then the next row is slightly longer. It can seat 4 more people. So that's going to put 22 people in that row. And then we just keep adding 4 each time. So 22, then 26, then 30, and then 34. So the total number of people, we just need to add these together. So real basic, we're just doing 18 plus 22 plus 26 plus 30 plus 34. Get out your calculator, add all those together. That should add up to 130. And that's it. So this is an example, though, of an arithmetic series. We have a sequence generated by each row, and it is an arithmetic sequence because to progress through it, we are simply adding 4 each time. And then if you add all the terms together, it becomes a series. And then if you need the sum of the series, then you just add up all those terms. So, very basic example. You might argue, well, why do we need to have any formulas for this? Well, this is a very small sequence. We want to be able to add up a series with, many, many different terms, maybe 50 terms, maybe 100 terms, maybe 1,000 terms, and we don't want to have to write out every individual term. We would like a formula that would just take us directly to the end. Just like we had for an arithmetic sequence, we had an explicit formula for that. We want one for an arithmetic series as well. Okay, so some new notation. When we were dealing with the sequence, we used a sub n to represent the nth term of the sequence, right? That was just the nth term of a sequence. We're using this basically the same notation, but we're going to use s instead. So s represents the sum of the first n terms of a sequence. Okay, so as an example, consider this series here, 5 plus 8 plus 11 plus 14 plus 17, and just on and on and on. So S1 would be the sum of the first term, meaning it is just the first term. S2 is 5 plus 8, which would be 13. S3 is the sum of the first 3 terms, which comes out to 24. S4 comes as the first 4 terms added together, which comes out to 38. And you could just keep this process going. S sub n represents the sum of the first n terms. And, I can't write what that last term is because I don't know how big n is. Now, I could put the formula in there for this particular problem. Remember, a sub n, in the previous section, we said is a1 plus n minus 1 times d. And we can't actually figure out what that is for this particular sequence. So a1 is 5. Plus n minus 1, we would leave that because that is the variable part, and then the d is 3. So this expression could be put here, but I can't get rid of the n. So, that big, nasty sum, even with this put in there, it's hard to wrap your head around that formula. It's not going to be easy to use. So we want to get a better formula for this. So we're going to use this as an example to generate the formula, and we're going to consider just the sum of the first 9 terms. This will establish a pattern that we'll be able to generalize into a formula. So S9 is just that sum of the first 9 terms of that same series that we had. So here's the trick. to come up with a formula, I've written out the sum here, and then I've written it a second time, but I've written it in reverse. Right? We know that's going to still add up to the same thing, doesn't matter the order, so I've just written it in reverse order. And what we're going to do is we're going to add those two rows down. So if you think of these like a variable, if I add them together, I have two of them, 2 times the sum of the first 9 terms. And then when we add down here, something interesting happens. Notice that you get the same sum every single time. It always adds to 34 when you add vertically down here. So just have a bunch of 34s. In fact, we have exactly 9 of them. This is the sum of the first 9 terms, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are exactly 9 34s, exactly the length of that series. So we could just write that as 9 times 34. Our goal was to get a formula for this. So what we can do to finish this is just divide both sides by 2 here. Right? Divide the 2 over, and we get this expression here. The sum of the first 9 terms is really 9 divided by 2 times 34. If we went ahead and did that math, that's obviously 9 times 17, which would be equal to, I believe, what's that, 153? So that is the sum of all of those. Now, for me, that computation is much easier to do than to actually add that up. I can do that in my head where I can't do this. So let's try to unpack this a little bit more. Where did the 34 come from again? Well, the 34 was the sum of the 5 and the 29. The 5 and the 29 are the first and the last terms. So I'm actually going to write that out. 5 plus 29 here. Okay, so let's try to change this stuff back into variables. The 9 was just how many terms there are. So if we're trying to do this in general, S of n, that would be the n. It's how many terms there are. The 2 is always going to end up being there because we're going to have that same algebraic process that's going to generate the 2. So it stays as a 2. What was the 5? The 5 was A1. So we'll put that as A1. And then the 29 is the last term, which would be the nth term, A sub n. So this gives us an explicit formula for the sum of the first n terms of an arithmetic series. Very nice closed form, enables us to go straight to the final answer. Now, because we don't like to make anything simple, there is a variation of this that you'll see on the next page here. So we can actually write this formula in 2 different ways. And that's because, remember, a sub n is equal to a1 plus n minus 1 times d, what we saw in the previous section. So what I could do is I could put this expression in right here. And if we do that, this turns into n over 2 times a1 plus n minus 1 times d, right? Because this is really a sub n. So I've just replaced that by what it's equal to. And now we have like terms here. These a1s can be combined. So we have a1 over 2, or n over 2 times 2 a1s plus n minus 1 times d. So this formula is the same as this formula. And sometimes this is going to be more useful, sometimes this is. So they're both equivalent. You need to know both of them. So they are written both here. So in general, you need to know n no matter what to use either formula. You need to know a1 to use either formula. So if you know the last term of the series, then I would use the first formula. If you don't know the last term, but you know the common difference, then I would use this formula. So let's try applying those in this, one of those at least in the example below. So it says consider this arithmetic series, or sequence, sorry. So this is just written as a sequence, but they want us to find a formula for the sum of the first n terms, meaning if you were going to add these up and you were going to go all the way out to the nth term, which we don't have here, what would be the formula for that? Well, since we don't have a sub n, we're going to need to use this formula here, which means we need to figure out what d is. But d is the same thing it was before. It's the common difference. What are we adding to move through this sequence? And you can see fairly easily d is equal to 4. Right? You can find that again by just subtracting any 2 consecutive terms. So it doesn't matter where you start, just so if I took 7, take the term before it, which is 3, that is equal to 4. So that's where d is coming from. It's what we're adding to move through the sequence. All right, we also know A1 is obviously -9, and we're going to leave n as the variable. So I'm going to write out just the general formula first, and then we can put in the things that we know. So it's n over 2 times 2a1 plus n minus 1 times d, and leave n as a variable, so n over 2 times 2 times -9 plus n minus 1 times 4. And this is it. This is our explicit formula, but let's clean it up a little bit. So n over 2 times -18 plus 4n minus 4, which then if we combine the like terms inside, that's n over 2 times 4n minus 22. Now, sometimes I'll stop here, especially if these don't divide nicely by 2, but we could go ahead and distribute here. If you distribute through, you're going to get 2n squared minus 11n. So this is the closed formula that will tell you the sum of the first n terms, no matter if you want to add up the first 5 terms or the first 1,000 terms. You just plug that number, whatever it is, however many terms you want, into this expression, and it will tell you what those add up to. So if we do that with 12, so the sum of the first 12 terms would be 2 times 12 squared minus 11 times 12. All right, now the numbers do get large pretty quickly, so most of the time we're going to just put this expression into the calculator. That comes out to 156. So again, that's if you wrote out all the first 12 terms, added them together, it would give you 156. Okay, let's try a different one. This one says find the sum of the first 100 positive integers. So positive integers, or in other words, natural numbers, we're trying to find 1 plus 2 plus 3 plus 4 all the way up until we get to 100. So we can use either formula here. Either one is going to work. So let's write down the things that we know. We know A1 is equal to 1. Before I even get to this, actually, we should establish that this is an arithmetic series. Right? It says it is, but we should prove that it is an arithmetic series. You should double check that. To be an arithmetic series, the numbers here, the sequence, needs to be arithmetic. And we can see that this is because to progress through this sequence, we are simply adding 1. So in other words, we know the D is 1. The common difference is 1. And then as we already said, A1 is also 1. And we know that the n for this, the number of terms that we're adding, well, there's 100 numbers here, so we're adding up 100 numbers. The other thing that we know is the nth term, which in this case is the 100th term, is also 100. Now, it is just a coincidence that these match. Most of the time, these are not going to match. This is the nth term, the last term. So in this case, it is 100. There are 100 numbers here. Right? The total amount of numbers is 100, and the final term is 100. Okay, so we could use the easier formula if we wanted to. Let's write that one out. So S sub n was n over 2 multiplied by a1 plus a sub n. In this case, that's S100 over 100 divided by 2 times 1 plus 100. All right, we're just plugging everything in. N was 100, A1 is 100, A sub n was 100. Okay, and then if we simplify this, this is 50 times 101, which is 5,050. So I was able to add up the first 100 positive integers without using a calculator. Right? Fairly basic math by just plugging into that formula. Now, you could have used the other formula as well, just to show that. S sub n equals n over 2 times a1 plus n minus 1 times d. And we would plug in, again, same numbers, 100 over 2, and then 2 times a1, that would just be 2 because it's 2 times 1, plus it'd be 100 minus 1 times d, and d in this case is 1. And then if you simplify this, you get 101 there again. So you end up with the same exact amount, 5,050. Definitely seems like this was cleaner, but both would work for this problem. Okay, so let's try using the sum formulas, but we're going to solve for a different term. So we are given here, it says the sum of the first 17 terms of an arithmetic sequence is 187. The 17th term is negative 13, and we're supposed to find A1 and D. So let's use the symbols here. The first thing says the sum of the first 17 terms is 187. That's one thing that we know. We know the 17th term is negative 13, and that's all we're given. So notice that the index on these matches. So it's going to be useful to use the shorter form of that explicit formula for the sum of a series, of an arithmetic series, which was this. So we know we're given S17, the sum of the first 17 terms would be 17 over 2, right, because that's the n value. We don't know A1, but this would be, not S, it would be A17 here, the 17th term. Okay, so then we can plug in the numbers that we know. We know this is 187. The sum of the first 17 terms is 187. Leave this as 17 over 2 for now. A1 we still don't know. The 17th term is negative 13. So I've just plugged in the things that we know. Now everything here is a value except for we have one unknown, which is A1, so we can go ahead and solve this. I would probably, just to deal with this divided by 2, I would multiply both sides by 2. You don't have to. You could divide here, but just need to be careful, don't do any rounding. So if you go ahead and multiply both sides by 2, we have 374 is equal to 17 times A1, we just write that as minus 13. You could distribute the 17, but it's going to be easier just to divide this over. 374 over 17, which comes out to 22. So 22 is equal to what would be left over here, which would just be A1 minus 13. Right, so again, if you're unclear what I just did there, I just divided both sides by 17. So that cancels to make a 1. This comes out as the 22. I'm going to erase this actually. Okay, then add 13 over. So we have 35 is A1. Okay, so we have that done. But now we need to go back and find D. So to get the value of D, we have several options, but one of them is just to come back to this. We know the 17th term. Actually, let me write this. We know the nth term from our previous set of notes was A1 plus n minus 1 times D. So the 17th term is A1 plus 16D, because you do 17 minus 1 there. And we can go ahead and plug in A17 is negative 13. A1 we just found is 35. And then we have 16D here. And now we just solve this for D. So subtract the 35 over, you get negative 48 equals 16D. And divide the 16 over to get D is equal to negative 3. So we have our D, we have our A1, the starting amount and the common difference. So it doesn't ask us this, but if it said write out what the series looks like, we could do that from this. We know it's 35. We're subtracting 3 from that, so it'll be plus 32 plus, keep subtracting 3, so 29 plus on and on like that. Right, that would be what the series is that generates the 187. If you wrote out 17 of them and added them together, that's where you're getting the 187. Okay, let's try an application problem. So this one says a radio station considered giving away 4,000 every day in the month of August for a total of 124,000. Then they decided they wanted to scrap that idea. They said instead they wanted to increase the amount they gave away every day while still giving away the same total amount. So they only have 124,000 to give away, But rather than just giving the same amount away each day, they're going to start with a lower amount and add to it, so each day the prize goes up. So the biggest prize then would be on the last day of the month. So they've decided they want to increase the amount by $100 each day. For each day of the month, they're going to add 100 more onto the pot, or the giveaway for the following day. The question then is, what should they give away the first day so that they're still only giving away a total of $124,000? Okay, so to make sure we're clear, this thing is out. We're not doing that anymore, right? It's not 4,000 every day. It's going to start with some unknown amount, which we have to find, and then we're adding $100 more each time. So the fact that we're increasing by $100 each day, each following day, this is what tells us that this thing is arithmetic. Missed my eye. So it's arithmetic, and we know that the D is equal to 100, right? That's what this is giving us. We also know that the total, all of it added together, is 124,000. So S sub n is 124,000. And in fact, we actually know what n is. We're doing a giveaway for every day in the month of August, so that means there are 31 days in August, so n is 31. So really, this is really S31. The sum of the 31 days totals up to 124,000. Okay, so we don't know what the first day is and we don't know what the last day is, but we have the D, which means we can use the second formula for the sum, meaning this formula, S sub n equals n over 2 times 2a1 plus n minus 1 times d. Right, we have all of the information for this except for the a1. So we can just start plugging the numbers in. We have 124,000 for the S sub n. The n, as we said, was 31. We don't know a1, so we'll leave that as the variable. We've got 31 minus 1, which would just be 30, so if you'll permit me to just put 30 there, times d, which was 100. So that's got everything plugged in. Now we can just go back and solve for a1. So again, I'm going to get rid of the 2 by multiplying both sides by 2. You could distribute 1/2 if you wanted, but we've got that'll be 248,000 equals 31 times 2a1 plus, and you can go ahead and multiply this. That's just a 3,000. You could distribute the 31 or you could divide it over. So to keep the numbers a little bit smaller, I'm going to go ahead and divide it over, and it divides nicely and comes out to 8,000. Right, now we have a simple equation to solve. Subtract the 3,000, so you have 5,000 equals 2a1. Divide the 2 over, a1 comes out to 2,500. So this is how much they should give away on the first day. So A1, they give away 2,500. Second day of the month, they're going to give away 2,600, and just keep going until you get to the last day. So the last day would be the 31st day, and we can actually figure out how much they're giving away on that final day as well. So we would use the A sub n formula. A sub n equals a1 plus n minus 1 times d. So it would be 2,500 plus 30, because it's 31 minus 1, times 100. So that's going to come out to, what is that, 5,500? So they start off first day giving 2,500, last day they're giving 5,500. So they didn't ask for that, but they just asked for the first day. Okay, so let's move on to summation notation, or it's also called sigma notation. So when we write out these big sums, it can be tedious and they can take up a lot of space, so it'd be nice to have a condensed way of writing it, and that's where summation notation comes in. So the sum that you see here, 3 plus 6 plus 9 plus 12, all the way up to 30, all that added together could be expressed using this notation here. We call it sigma notation because the letter here that looks like an E, that is the Greek letter sigma. It's the capital version of sigma. So this just stands for the shorthand for this sum. So let's break that down. Okay, so we've got the summation sign, which indicates sum. And then we have what you see down here is the index. This is saying what are you actually incrementing by. So we're saying n is the index, and we're going to start with the first value of the index being 1. And then the top number is how high does the index go? What's the highest that n becomes? And in this case, the highest it becomes is 10. The way you would read this is it is the sum of 3n as n goes from 1 to 10. And let me go back for a second. Again, the idea, the way it works is if you were going to expand this out, if let's say this wasn't here, then what it's telling you is start by plugging 1 in. So 3 times 1. That's your first term of your sum. And then you increment by 1 each time. So the next one would be 3 times 2, and then 3 times 3. And then you would just keep going until you get to the last one, which would be 3 times 10. And that's where these numbers are being generated. This is the 3, the 6, the 9, the next one would be 12, all the way up to 30. So it's just a generator to generate this sum. Okay, so let's try practicing expanding these out. So we're going to rewrite it as a sum, and then we'll go ahead and add it together. Okay, so on this one, k is the index. You can use whatever letter you want as the index. They just have to match. So common letters for the indices would be, I, J, K, N, M. Those are probably the most common used indices, but technically any letter can be used as an index. Okay, so the first term would be 2 to the 0, plus, then we increment 2 to the first, plus 2 squared, plus 2 cubed, and we stop there because the upper limit for the sum was 3. So this is expanding it out as a sum, and then if we evaluate it, we're just doing the math. We're actually simplifying it. So I'm going to simplify each individual term first. So 2 to the 0, we know that anything raised to the 0 power that's not 0 already is 1. Then 2 to the first is 2, plus 4, plus 8. And then if you go ahead and add all those together, that looks like that's 15. So this entire thing, the answer to it is really 15. All right, let's try the next one. Okay, so first term is 3 plus 1. Notice this index starts at 1, where the previous one started at 0. Your lower limit can start at anything. Okay, so we've got 3 plus 1 is the first one, then 3 plus 2, plus 3 plus 3, plus 3 plus 4, plus 3 plus 5. So that would be expanding it out, and then simplifying it. This is obviously 4 plus 5 plus 6 plus 7 plus 8. Notice this one is an arithmetic series. Right? We're incrementing by 1 each time, so you can actually write arithmetic series using summation notation, as we'll see more of later. Okay, if we add this one up, this one comes out to 30. All right, then the last one, let's just change colors just to keep it separate here. Notice the index on this one is starting at 5, so this is going to be 3 times 5 minus 4 minus, I need to make sure that's clear. Let's do a better job here. All right, next one is 3 times 5, 6. 3 times 6, we got to increment. 3 times 6 minus 4 plus 3 times 7 minus 4, and we're done. Right, this one just went up to 7. So I kept these really short just so we didn't have to write too much out. Okay, so then if you simplify 15 minus 4, you get 11, plus 18 minus 4 is 14, plus 21 minus 4 is 17. Notice again, this one is arithmetic. Notice what the common difference is. The common difference is 3, which we see sitting here. The common difference on the previous one was 1, which you actually can see right here. It's the coefficient of the I. So we're going to come back to that in a minute and emphasize that a little bit more. If you add those together, you get 42. Okay, so that's expanding and then evaluating them. let's try to go in reverse, meaning I'm going to give you this, and we want to try to write it back in this form. This is what's truly difficult. We won't do a ton of this, but it will be helpful for things we do later on. So here is a series, and we want to try to write it in sigma notation. So what we need is we need some way to generate this list of numbers, some formula that generates it. In particular, we need an a sub n formula. Now, many of these are arithmetic, but they don't have to be arithmetic, and we still want to try to come up with a formula for it. So these first couple ones, we're just going to try to do by inspection, and then I'll give you some hints that can help you generate the formula maybe a little better. Okay, so this first one, I noticed these are all multiples of 5. So naturally, I would say we could just do 5 times, actually I'm going to change the index just to make sure it doesn't confuse you. We're going to actually use k as the index instead. So 5k, right? This is meaning 5 times 1, 5 times 2, 5 times 3, 5 times 4, all the way up. So the summation could be, I'm using k as my index. I'm starting at 1, and my generator is the formula 5k. And then I have to figure out, well, how high did it go? What value of k generates this? Well, 5 times 6, right? We did all the multiples from 1 up to 6. Notice there are a total of 6 terms. 1, 2, 3, 4, 5, 6. 1 to 6 is 6 terms. So that is our answer. Now, one thing that makes these confusing is they're not unique. There's actually infinitely many ways that you could write this formula. So as an example, let's make a variation of this. Let's just say that for some reason you insisted that you needed the index to start at 0. Well, then we would need to modify the generator, and we can modify it fairly easily just by adding 1 to it. So now when I plug 0 in, the very first one is still going to be 5 times 1. We're still going to get this. But since I've modified the lower bound, I have to modify the upper bound. I can't put 6 here because I would be really doing 5 times 7 on the last term. So that means the upper limit would actually stop at 5, because then it would be 5 times 6, which is what we want for this. So both of these are actually valid answers. And we could come up with infinitely many more that would also be equally valid. So we're just looking for at least one that works. Okay, let's try the next one. So the next one, you can see we are starting at 201 and we're adding 1 each time. Okay, so what I would probably do is I would say I would probably start at 200 and say that we are adding k to it. This is the generator for this formula, so that the sum could be the sum of 200 plus k, where k starts at 1, so we have 201 as our first term, and then the last one that we're adding is 6. So kind of similar, basically the same limits as the previous one. This would generate this expression here. And again, you could modify it. You could do something different. We could say, okay, we're going to start at k equals 0, then it's going to be 201 plus k, and this is only going to go up to 5 then. So again, infinitely many ways you could write that. Okay, so let's look at the next one. The next one's a little bit trickier. It's kind of hard to see what to do here. But what I do notice is this is arithmetic. So as we progress through this, I can see what we're doing is we're subtracting 9 each time. Minus 9, minus 9, minus 9. So it's arithmetic, which means that to get the generating formula, I can use the a sub n formula. So remember, a sub n is a1 plus n minus 1 times d. So let's just put in everything we know. Well, a1 is 38, and we'll leave n minus 1. The common difference we just said is negative 9. So let's simplify this. So we end up with 38. It will be plus 9 minus 9n when you distribute. Reordered it there, but go ahead and putting those like terms together, you're going to have 47 minus 9n. This is our generator. Since I've got it with n here, I'm going to go ahead and use that as my index. So 47 minus 9n. I'm going to start with n equal 1, and I'm going to go up to, well, how many terms do I have? 1, 2, 3, 4, 5, 6 terms. So this would be one possible answer, but as with all of them, it's not the only one. If again you wanted to start from 0, we could do start at n equals 0, and then that if we're starting with n equals 0, I'm going to put a 38 here and subtract 9n from that. Notice if I put 0 into this, I'm still going to get 38 there, but then I'm going up to 5 instead. So equally valid, but this one's probably easier to generate. So if you see that the sequence is arithmetic, you can use this strategy. That same strategy could have been used on both of these as well, because they are both arithmetic as well. On this one, the d was equal to 5. On this one, the d was equal to 1. Okay, last one. First thing we should look at is it arithmetic? And you can see that as what adding here, you're adding 5, and then you're adding 7. That's not arithmetic, so that's not going to work. So we need to come up with something else. This is a very common one that I give to my students a lot, and even in my calculus class, a lot of times they sit there and stare at it and they just can't see what the pattern is. But I would hope that these numbers jump out at you. There is something special about all of them. They're all perfect squares, right? This is really 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. So that means the generating formula, the a sub n formula, is really n squared. So we could write this as the sum of n squared, where n starts at 2, my first base there, and the base goes up to 7. And again, we could modify this. If you really needed the index to start at 1, we could do n equal 1, but then we would have n plus 1 in parentheses squared, and that would go up to 6 then. Plugging 1 into this, we'd have 1 plus 1 squared. That would give us the first term. Put 6 in, that'd be 6 plus 1 squared would give us that last term. So either of these would be valid, and you could come up with other ones as well. All right, so you should see some of these in the homework. Okay, now, if you recall, in a previous set of notes, we said that arithmetic sequences, which have this formula, are basically linear equations. And the way I tried to convince you of that is I rearranged this. I distributed the d in there so that you would have a1 plus d times n minus d, and then I reordered it, dn plus a1 minus d back there. And then we just said, okay, this is a constant number, so we just called that c. So we had d times n plus c. Right, that is kind of an equivalent formula to this. And we said, well, n is like our variable, so this is like having y equals d times x plus c. So d is the slope, and then this is some y-intercept. But the important thing is that an arithmetic sequence is really a linear equation, and the slope, or the coefficient of the variable, in this case the index, is the common difference. So that's going to come up again here. So what I'm getting at is anytime you have a sum that is in this form, where it's a number times the index plus another number, right? Anytime it looks like that. So for example, what I'm saying is if it's like 7i minus 35, where I equals 1 up to, it doesn't matter, 100. This has that structure. That automatically tells us that this is an arithmetic series. Because this is a linear expression, right? Its highest power is 1, so it's just like having mx plus b type expression there. So we automatically know that it's arithmetic, and we also know that in this case, the d, the common difference, is 7, right? It's the coefficient of the index. That is the common difference. So that means we can use the formulas, we can use the SN formulas that we've been talking about in this lesson to evaluate any type of sum that looks like this, anything that has this structure. So let's try doing that here. So notice this matches the structure of that, means it is arithmetic. So let's write down what we know. We know the common difference is 4. We know A1 we can find by just plugging the 1 in, which comes out to 12. 4 plus, you plug the 1 into this, 4 times 1 plus 8 is 12. Right, that's where the A1's coming from. And we can also find the last term. And when I say the last term, in this particular case, I really mean the 10th term. Right? There are 10 terms to this. It goes from 1 up to 10. The 10th term is found by just plugging 10 in. So we would have 4 times 10 plus 8, which is 48. Okay, so that means the whole thing, right, this really is S10. It's the sum of the first 10 terms. So to remind you, the general S sub n formula is n over 2 times a1 plus a sub n. And in this particular case, we're looking at the sum of the first 10 terms. So it would be 10 over 2 times a1, which is 8, plus a sub n, which is 48. And then we just need to evaluate this. So this is really 5 times 56, which that should come out to 300, I believe. So this sum we can do without expanding it. We can just simplify it using the formulas that we've already gone through. If you didn't want to use this formula, we could use the other variation. So n over 2 times 2 times a1 plus n minus 1 times d. We have all the information to plug into this, and it will give you the same final answer. I'll let you do that as an exercise if you want. So either formula will work. If you don't want to have to think about finding a sub n, you could use just these two pieces of information and go straight to this. It's just there's a little bit more computation on that part. Okay, let's try another one. And maybe on this one, maybe I'll write it using that formula. So we know the a sub 1 is found by, first of all, I should back up. Notice this is linear. Just like this one, it's flipped around, but it's still a linear expression. A1, the first term, is 4 minus 3 times 1. We find that just by plugging 1 in. So that comes out to 1 for this example. The common difference, again, is the slope of this expression, right, or the coefficient of the index, the variable term, which in this case is negative 3. If we needed the 50th term, the a sub n term, then we would plug 50 into this expression. So we would have 4 minus 3 times 50 on that one, which is negative 146. But let's try not using that on this one. So we're going to just use the first two things. So I'm going to go to the S sub n equals n over 2 times 2 times a1 plus n minus 1 times d. So we don't even need to worry about doing that part there. Okay, so n, I guess I should have written that down. N was 50. Just like on this one, I should have written down n was 10. So you have 10 over, now I'm mixing them up, 50 on this one, over 2, multiplied by 2 times a1, which is 1, plus 50 minus 1, multiplied by negative 3 on this one. All right, so you can go straight to the formula, but the math inside's a little messier. So this is going to be 25 times 2 plus, 49 times negative 3. And then if you want, you can go straight to the calculator on that. I believe that's going to be 25 times negative 145. Which comes out to negative 3,625. So that would represent the sum of all those 50 terms. And we did that without writing any of them out. All right, that completes this set of notes, so hopefully this was helpful. If you do have any issues with the assignment, make sure you email your teacher.